Okay, welcome everybody. Thank you so much for coming. This is Open Research Institute's Projects Meetup for the 27th of January, 2026. What we do at this meeting is talk about what we have done over the past week or so, what we have planned to do over the next week, if we need any resources that ORI can provide, and if we have any roadblocks that we need help with. And so that's the format of the meeting. And what we'll do is we'll open the floor to anybody that has any time constraints. All right, go ahead, Aaron. You have the floor.
Sure. Hello, everybody. So I made a little bit more progress with the OpenCPI implementation of the DVB-S2 encoder on a Xilinx ZCU 104. Last week, I reported that I was having issues with using the Axie4 Lite registers, and all the registers were being set to 0. I did that. Well, what I found out was that I had a optional configuration in OpenCPI that wrote zeros to all the registers. It was a default value to 0. So I removed that, and that solved that. So now I can set the registers correctly and not be afraid of it messing up by them all being reset to 0. But looking at the register set, it didn't look like it was going to have a negative effect either way. But that was resolved. So now I can read back the config register with after its initial power on, and read a value of 1, which is a positive sign. So now I moved on to trying to get data to flow from the FPGA and from the CPU to the FPGA using the GSE padding. And that's what was my next blocker. But then that turned out to be because in OpenCPI, the worker that I compile, when I did my initial testing, it was against the 64-bit, the host that does all the building. And so I did all my changes there, and I wrote everything to a file, like I said last week, and I can see that the padding was being added as over and over again. But when I went to hardware, I only got one message to be sent. So what I failed to do was to rebuild for the ARM architecture, ARM64 architecture, and use the latest build, basically, that not continuously sent GSE padding messages. So then I got that working. So now I'm sending padding data from the CPU to the FPGA, and I verified that it was being received on the ILA, using an ILA in the FPGA fabric on the FPGA side. But then if all was working, I would be able to see some spectrum on the output of the 89361, which I'm using. And I'm not. So that's where I'm at. I'm going to spend this week debugging why I don't see any samples being generated from the encoder. Well, identify whether that's the case or it's something along the chain all the way to the RF. So that's where I'm at.
Okay, wow, that's a lot. And to just put this into a little bit of context, the OpenCPI, I think if you want to say a couple of sentences about OpenCPI to introduce it to anybody that might not be familiar with it, now would be a really good time. But also the continuous data problem. This is sort of the way that our downlink for DVB-S, DVB-S2, DVB-S2X, the way that it works is that it's always on. So the idea of filler dummy frames, making sure that there's data in the pipeline at all times is actually really important and becomes it's a tripping point for a lot of us. This is something that may or may not be seen in a lot of packet-based or burst-based modems. But the design of DVB-S, DVB-S2, it's a continuous downlink that there's always going to be something there in the downlink. And it sort of sounds like to me that this is the thing that you're grappling with. So please correct me if I'm wrong on that.
No,
And,
that's fine. No, you're right.
and go ahead and
So
tell people about OpenCPI. They're not familiar
okay.
with it, because it's really, really cool. So it's floor is yours.
So yeah, OpenCPI stands for Open Component Portability Infrastructure, and it's an open source project that allows you to um, take advantage of hardware, and it's hardware agnostic and platform agnostic, meaning that it's not built for EDS radios or the Libre SDR or the Flu SDR. It's a framework that allows you to build your application once and then be able to deploy that application across a very diverse set of hardware. So right now I'm working on the ZC104, and it's utilizing the Zinc UltraScale architecture. But after I've solved it for the 104, it can be applied to others of the Zinc UltraScale architecture. And then OpenCPI has the ability to target the Zinc 7000 series. So that's the 7010, 7020. But right now the encoder specifically is for the Zinc UltraScale. So it's similar to GNU Radio, such that it breaks pieces of your design into smaller blocks, DSP blocks. But the difference between GNU Radio and OpenCPI is that it allows you to generate your blocks for FPGA resources, FPGA. And one of the uniquenesses of OpenCPI is that you start with a component. I've said a component, but a component is just a specification, just defining its inputs and outputs and its property values, like tuning knobs of that particular component. But you build an implementation called a worker for either the FPGA or the CPU, or you can have both, and then that allows your application to target different, not only different architectures, but different sizes of hardware. So in Opulent Voice, we see that we've outgrown the Pluto SDR and its FPGA resources. But one of my long-term goals is to get Opulent Voice working with OpenCPI as well. Would be to have break a little bit of the framing into the CPU so that way the application can run some of that on the CPU side and then do the MSK on the FPGA side, and that would open up the Pluto back up as an available resource of running Opulent Voice. But in a nutshell, OpenCPI is a framework that targets FPGAs and CPUs, and it's not specifically use case is not for software-defined radios. It just happens to be the application that we try to expose the framework to. But so yeah, that's a little bit about it. There's a lot more, but yeah.
Thank you so much. I think that what you're
Yeah.
doing at OpenCPI really gets at the heart of a lot of computer science work right now, which is heterogeneous computing, meaning doing computing not just on a general purpose processor, but on FPGA, ASIC, and also GPUs. And yeah, OpenCPI is solving I think, some of the most hardest problems in computer science right now, which is how to distribute the computing load to the hardware resources you have without a complete porting, redesign, a lot of messy, hard, awful work done by people. It's not a solved problem at all, and is something that you mentioned GNU Radio. GNU Radio has grappled with this um, and tried to address it. And we can see some of the results, like in RF knock versus the traditional GNU Radio blocks. They recognize this is a significant problem and have talked about it at their conferences since 2016. So any forward progress here and figuring it out, making it accessible, and definitely an open source solution is really pretty much at the forefront of computer science in my opinion. So hard work, and I think you're going to get an awful lot of attention if I know you already have it, and OpenCPI is appreciated, but this really is one of the third rails of computer science. It's incredibly difficult work and deeply appreciated. So we're happy to help, and we really appreciate you being here and talking about it. So thank you. All right. So yeah, OpenCPI, if you have not already become familiar with it and you're interested, it's opencpi.org is the website, and there's a really good set of resources there for onboarding and getting familiar with that tool framework. All right, let's talk a little bit about Opulent Voice. I can give a brief report. So we revised the protocol specification for Opulent Voice, which is our uplink. That's what we use for our open source satellite work. This is the digital or native digital uplink for our open source HEO, GEO, et cetera, satellites. But it also is totally appropriate to use for terrestrial communications, either point to point, which is kind of what we're trying to demonstrate through the lab calls right now. Paul can probably speak to that most directly. But we can also deploy this in terrestrial repeater networks that are essentially a satellite simulator. So conference-based or repeater-based system or point-to-point links. The biggest distinction for Opulent Voice from all of the other, and there's quite a few digital voice modes that if you're in amateur radio, you might be familiar with, like P25 or DMR, D-Star, Yaesu System Fusion. The other open source alternative is M17. We emphasized and prioritized audio quality, and this meant going to a better vocoder, so a higher bitrate vocoder. So we went up to 16 kilobits per second from around about 3,000 um, bits per second. This means that the bandwidth increases, and so our null to null bandwidth for our particular protocol is 81 kilohertz rather than 9. So what do we lose? We lose 2 meters. So we lose VHF, but it's legal on UHF and above. And the demonstrations that we're doing all throughout 2026 will show that it works really well, coexists, improves things. Another big reason for doing this, because there are other alternatives, is that no other protocol has voice and data and keyboard and control and authentication and authorization all integrated in a way that doesn't require you to switch to a second clunky packet mode or to handle the authentication and authorization essentially out of band. So those are the two big innovations that we bring with Opulent Voice, and those things are going to be demonstrated throughout 2026 to a lot of different people. So the spec has been revised. It's at 1.1 is what we called it. It's out for review. So the link, it's in the repository, it's in Slack. The changes from 1.0 to 1.1 were to revise the randomization, which is now a CCSDS standard linear feedback shift register rather than just a list of random numbers. The forward error correction has been clarified for just to fully specify it, because it was kind of vague in the original spec, in the 1.0 spec. We're using the NASA convolutional code. And to emphasize that soft decoding will get you the full coding gain. The sync word has been included and revised, the one that we found through exhaustive search, and the correlator approach has been defined there. And the interleaver, we abandoned a non-optimal interleaver and we went with a really good row column interleaver. So the simpler method actually turned out to be the better one for us, just simply because of the length of bits in the packet. So it's now a row column interleaver rather than a more complicated polynomial. So those are the updates to the spec. We also removed a couple of sections that were speculative, talking about future work or, insinuating that you can have different, options that, these are all really that are implementation specific and don't need to be in a protocol specification. We want to clearly communicate what you need in order to interoperate with Opulent Voice. So interoperability was the motivation for updating the specification. It's now completely updated. This feeds into the FOSDEM preparations. FOSDEM, big conference for open source, free and open source developers. And it is in Brussels, over in the EU. And F5OEO. This is Evariste. He's very graciously agreed to present for us in person at FOSDEM, and we are very much looking forward to sharing the work on this particular part of our design. And it's only 4 days away. So the slides have been completed, and we're going to go ahead and now cut them down to where they're a little simpler. We went ahead and made a very full set of slides with lots of implementation details from Interlocutor and Dialogus and Locutus, the modem. A lot of that stuff can be in slides that can be shared with the community after the talk. So people often ask, hey, do you have a set of slides from your talk? And we can say, here you go, here's the full set of slides. But the ones that need to be shown on the screen probably need to be simplified, like a lot of the block diagrams that go through, what interlocutor does and the different functions that need to be called. Those are fine to share later, but we can back out of doing that and then to reduce the bulk on the screen. So that's what's going to happen over the next day or so. And yeah, just a big thank you to Evariste, who's here with us today, for agreeing to do this. Really looking forward to hearing feedback and questions from the community because they are. This is a very, very active community and a really big conference in open source work. So I'm going to pause here. I hand the floor over to Evariste and then Paul and then Matthew and anybody else has any questions or any input or any content about Opulent Voice, then you're absolutely welcome to take the floor. So off to you, Evariste.
Okay, thank you very much. Thanks for all the work you've done on the slides, which is very good. Yes, need maybe to short and to sum up because nearly 40 slides in 25 minutes is a lot. I hope that I can show it with all the question in mind and be sure to have the main what we want to transmit to the open source community. Well, what are the key points of the modem, and yeah, this kind of thing. Unfortunately, I didn't have the time to ask you some other question about Opulent because I need also to prepare my my presentation, which is the afternoon, dealing with the Pluto SDR clones, which mean library SDR, etc. But yeah, all seems very good on slide, and it's good that still working on the protocol. And if I have reached or not reached, but suggest some way of thinking, because sometimes when you write protocol, it's not well. You can't think about all the user cases, and yeah, it was good to have some discuss about very simple cases, but have in mind all that. So thank you very much.
Yeah, sure. And then just in case y'all don't know, Evariste has two talks at FOSDEM. So please make an effort to check out the schedule and watch either his talk about his work live or make sure to check it out when the recordings are posted because it's pretty amazing stuff. And thank you again, Evariste. Very much appreciated. All right, Paul, to you.
I have made a first pass through your revised protocol spec, and I do have some comments and things I want to talk with you about. I'm going to need to go through it again before we do that, so that I know what I want to say. There's lots of good stuff in there. It's an important document. Important to get it as right as we can, as well. We did make some lab conversations here, but nothing new since the last time we spoke a week ago. So I'll go ahead and pass it over to Matthew. And thanks to Evariste for taking over the talk at FOSDEM. That's great.
Oh, and I think Matthew also has some things to talk about because he's started work on, or I shouldn't say started work, but he's continuing work on the symbol lock. So we've spent time talking about the frame lock at the frame level to determine whether or not you've locked in on the frame. But before that has to happen, you need a good symbol lock from your receiver. And so this is an area that he's been investigating and researching for quite a while. And I think he's now engaging in an actual branch and development that will you'll see in the repository.
All right, good morning. Yeah, I've been able to start some implementation for the symbol lock, just in very early stages right now, but I have some simulations up and running and looking at it. I think we probably can get something rudimentary working here in short order. I'm hopeful. And then I think some further analysis will be useful, and I want to add to it an SNR, or at least an EVM type calculation, so that we can get a sense of the symbol qualities, from a having that metric for what the link quality is directly. So I think that's something else I want to include in this work. So I think I have a start on it, and hopefully the next few days I'll have something we might be able to test in the lab if I can get enough time to move it forward.
Awesome. Thank you so much.
And I will say also, I'm hoping to, write something up, at least for the newsletter, as to what it is, why we would do it, and how it works.
Outstanding. No, that would be super helpful. Yeah, we are putting together a newsletter for January. We always try to get it out in the actual month that it is declared to be in, and sometimes this happens, and sometimes it edges into the next month. But it's looking pretty good. This particular issue is ever so often we do a theme issue. So since there's been an awful lot of debugging to get the port from Pluto SDR over to Libra SDR for the FPGA heavy implementation, there was an awful lot of very interesting debugging. And so we tried to capture that and make sure it's in the newsletter. And there's also some other content. So there's some essentially some regulatory article with I would say that this is maybe not entirely non-controversial regulatory stuff about business incursions on the 70 centimeter band. This is terrestrial sort of business. So we're looking at an article from there. And then it would be really nice to have a sort of a technical explanation of, why do you care about symbol lock? What is it and how you achieve it? Some math and everything, and that would be awesome. So yeah, looking forward to seeing more about that and to be able to share it with folks in our community. That'll be great. Okay, so one of the other things that we're doing is we are very interested in supporting and helping AMSAT UK with their FunCube Plus satellite. This is under very active and aggressive development to get it ready for launch. And I'm going to go ahead and hand the floor over to Martin, M0LNG, and he's the lead for the digital experiment that is going to be on the FunCube Plus. And this is the MDT, or Mode Dynamic Transponder. And we have a couple of different simulations or models that we're developing. Probably the earliest one was just assuming that this was a communications service to translate different existing communication services, and that's not exactly what Martin was after. So he's more after weak signal work, digging things out of essentially a passband, and that's very exciting to us. And we actually have we could contribute here. So what we interpreted this sort of desire to be would be a successive interference cancellation sort of implementation. And so that's looking pretty good so far. I've shared the simulations and the models with Martin and David and others. And I'll just turn the floor over to Martin to correct us or to guide us, to give us feedback and to let us know how it's going.
Yeah, thank you, Michelle. First of all, yeah, sorry I've not been on the calls for a little while. I've been not very well out of action for a bit, but I'm just sort of catching up on things. I've got your polyphase channelizer IPython notebook up here. Been looking at that. You know, this idea of sort of 3 to 4 channels, you know, within the sort of 30-40 kilohertz bandwidth being what's achievable on the ICE 40. You know, sort of tracks with what we said before in terms of that being the number of signals. You know, anything more than one, anything sort of improving on the sort of green cube situation. You know, being what it makes sense to try to achieve here. I mean, from my side, you know, to move this forward, I need to progress the sort of hardware side of things, and sort of get out of the chicken egg of, okay, what hardware are we building, so what can we do with it, versus, you know, what are we trying to do, so what hardware do we need? And you know, so I'm also looking here at sort of, you know, how many bits of sample, like you've gone for 16-bit samples, which you know, tracks with you know, we can kind of do whatever in terms of ADC, in terms of sort of how much power or you know, so on we want to throw at it. But yeah, there's a lot of you know, sort of open questions here that I'm still trying to get my head around exactly how we would go about getting from, okay, here's some maybe hardware and here's some maybe bits of implementation, to how do we put this together? And that's kind of just where I'm at the moment.
Yeah, I have nothing but empathy because it's an impossible situation to have. Like you have the world as your oyster, right? And we live in a golden time for software-defined radio and for embedded processing and for, you know, easily accessible FPGA designs. But in defense of what you've already got and what you've proposed, it's a little different than what we do. So we tend to be very heavy on the FPGA and use you know, the general purpose processor companion, the computing companion, as kind of like, okay, anything that the FPGA can't do, then we'll offload to the general purpose processor. And I know some people on this call are cringing a little bit about that, you know, being that blatant about the bias here. And not everybody at ORI shares that bias, but in general, we really kind of like use and emphasize the FPGA. In your design, it's, I would say the opposite. The STM processor is extremely capable. It's very powerful. And the ICE 40 tends to be a little bit small. And the reason for this is that if you're going to put it on a small satellite, the power consumption is a huge factor. And the like the Zinc 7020 that we're now using in a any reasonable sort of like hardware implementation of a Zinc 20, you know, in a 9361 type of system, meaning like a Pluto-ish or a Libra SDR or Pluto Plus, is 2 watts plus. Now you can get it a little bit below 2 watts, but it's not going to be anywhere near the half a watt that you've got very achievable with the ICE 40 and an STM, whichever one of the STM. Like it's a very capable STM. So this means like more stuff needs to be done in general purpose processing, and the FPGA is now like an accelerator or a coprocessor, a traditional like math coprocessor. So this is super challenging and cool to us, and we get it, and we can see where we can really utilize the snot out of the ICE 40 to get the results that you want, which is a weak signal sort of receiver in space for amateur communications. And I think we can achieve that. And I would encourage you to just go ahead and make a call. Say,
Yeah.
we're using this, we're using that. And I think the biggest call you probably have to make is whether or not you're going to have those external ADCs or analog to digital converters because you have a very upgraded, very high precision ADCs penciled in, and you're not using the native ones that are already included, I think, in the STM. Or correct me if I'm wrong there, but you went
No,
ahead
I mean
and
that was a sort of point of trying to sort of prototype what a sort of high precision baseband that could be reused in other ways would look like. But what's there, doesn't have to be operated at full precision. Either if we only want 16 bits, we can run 16 bits, or we can run maybe sort of like 24-bit, but then just shift according to whatever signal level we want. So sort of doing digital AGC before it goes into the sort of 16-bit pipeline. What I'm trying to think about in terms of how it affects the hardware design is the sort of data flow. So if we envisage the FPGA being used for something like this channelization, then we could have the raw sample data from the ADC flowing first into the FPGA over I²S, and then the channelized data would be going perhaps over SPI to the microcontroller. And then if we assume the FPGA is not involved in the TX path, then because TXI is a lot simpler, then that could be, I²S going out of the microcontroller to the DAC. And it's just this sort of what do we route to what, and I've tried to sort of make that as configurable as possible, but there's a kind of a limit to how many options you try and squeeze into the layout. So if this, because when I first conceived this, it was like, well, we'll put an FPGA in there and we can use it as an accelerator for whatever. But I didn't have a very clear idea of what part of the system we would want to use that for, right? So using it for channelization, so that you've got effectively sort of 3 or 4 channelized sample streams coming into the microcontroller, it is a good answer for that. I wonder whether you think that's the only answer, whether you think that's the only thing that makes sense to use the FPGA for, or whether we might want to do anything else with it.
Yeah, that's a really good question. I'll go back to our original in email, where it was like, okay, so now I get it. Do you want to do essentially weak signal work and this sort of thing, and that the ICE40 is absolutely capable of traditional modes too. Like when I say traditional, like the traditional sort of digital modes that you would find from other amateur payloads or amateur terrestrial work. So it's fully capable of doing that. When we talk about successive interference cancellation and digging signals out, what we're talking about is taking a chunk of bandwidth and we're brute force searching and we're picking out the highest energy, like which signals peak up. This is sort of the equivalent of you looking at a pan adapter and going, oh, that looks interesting. And oh, that looks interesting. And one by one, you're going through and figuring it out until you run out of time. So,
yep.
That's the sort of thing that we're talking about here. But in earlier conversations, it's fully capable of handling a mode dynamic transponder approach to traditional modes. So it's not just this particular solution. This is the one that most closely matches your vision for the payload and what you would really like to see. This is your highest priority, but it isn't the only thing that the FPGA processor system that you have designed can do. And this opens up the question of like, can you reconfigure it in orbit? Like once it's launched,
Yeah,
yeah, reprogram the bit stream to figure it out. And if you can, then pretty much lots of different things are available to you. Um, so no, it's not limited. It's just limited by how easy it is to configure once you launch it.
yeah, okay. Um,
And I'm pretty
so
sure that people on this call, there's a lot of folks on this call that have a lot of experience with, near Earth launching, sounding rockets, LEOs, HEOs, and more, and lots of terrestrial experience that could look at the design that you have, which is a ICE 40. So I would call it a small FPGA, but honestly, it's really quite capable and a very powerful, good embedded processor. And then also you're opening up the option of having upgraded analog digital converters. And they would look at this and go, oh, basically this is a really solid design. So I'm sure there's folks here that could come up with even more uses other than a traditional multiplexing transponder for known modes, or a let's go out and look and see what we have. And there may be even more that you could do with this. So it's solid design. I would just go ahead and pull the ripcord and say we'll move forward on making it. And it won't be perfect, but it's really good.
yeah,
And
we've got the meeting coming up this weekend. I don't know if I'm going to be able to get there in person, but I'll see if I can at least join remotely with the other folks on the FunCube team, and that's going to be to sort of start hashing out some of the detail of FunCube Plus. And so I suspect that one of the things that's going to start coming out of that is the sort of you know what are we actually using all of the signals on that PC104 header for and everything like that, who gets what and so on. So
yeah.
um, I suspect it makes sense for me to transition this design to the CubeSat form factor before moving forwards, given that we're talking about needing stuff working on the bench by October. Rather than going ahead with the sort of dev board thing that I've got here, because I think a lot of the thinking has moved forward a bit, both in my mind and from sort of what you folks have brought to the table in sort of sort of refining the thinking on this. And we don't need as high end a baseband implementation as what's on that dev board design at the moment. We can probably save a bit of power by changing some of that. So I want to have another pass at that, I think, before trying to go to hardware here. And so I think the aspects that I'm most interested at the moment is sort of what what changes we might want to make to that, and what things we might want to see in that hardware design to make it a good platform for the sort of range of sort of use cases that we've talked about, from sort of fixed modes to weak signal work.
Okay, very good. Yeah, I see no problem with doing that. I think that I would be happy with a dev board that was in the 1U form factor. That would be totally fine. I think most people here would be totally comfortable with that. So I think skipping over like a spin of the board that was just sitting on your desk, and that's totally okay. And I'm comfortable with what you got so far. I do think that ADCs are, I mean, as we talked about, maybe overkill. Like we can't take advantage of that much. Um, that would be my instinct today. So if there was any place that you needed to kind of roll back, that you needed to offload and get rid of some power consumption, that we can make up for that. And we don't really need to make up for it, but it may not be something that we can fully utilize, maybe too much overhead. So I want to pause and make sure that anybody that's familiar with the design can go ahead and correct me if I'm wrong about that. Um, so that we give Martin the best possible advice for the meeting that's coming up real soon.
I mean, one thing we could do is go for one of the combined audio codec parts that has both ADC and DAC in one part. I went for separates because, you know, this partly came from some other board of ideas I had about radio design and trying to develop a really good high precision baseband, almost sort of like a reference design that could be used for lots of other things. So it's a little bit out of place in this sort of CubeSat context, but in practice, it's things like it just doesn't use that much power in the first place. Like even running this in 24-bit ADC is only 13 milliamps at 3.3 volts. So it's not something that's going to make a huge difference to power what we go with there anyway.
Okay. No, that sounds okay. That's good. All right. Anybody have any feedback about this particular decision? That's maybe some general advice or any sort of advice for Martin moving forward. It'd be really nice to keep the high end and high precision ADC. That's for a receiver. That's kind of one of your
yeah. On the TX side, though, we don't need a high precision DAC. Right, there's no real reason for that. We could probably use the one built into the STM32. Like I'm not sure exactly what the specs on that are, but it would do, you know.
Right. Yeah, I think emphasizing receiver performance is probably what we want to do. So
yeah, I see in the chat asking, you know, I assume ICE40 follows the KISS principle. The choice of ICE40 came down to, you know, what FPGA can we put on there in the power budget? I wanted to use one of the ones that works with all the open tool chains, which, you know, brought the choice basically down to ICE40 or ECP5. And ECP5 is basically just a bit too power hungry to do that kind of power budget. And then within the ICE40 product range, there's a few different parts with different numbers of up to about 8K LUTs. But there was a choice for the package reasons to go with the biggest one you could get in a QFN, where all the solder joints are inspectable. Yeah. As opposed to a BGA package where you need the X-ray to tell if it's good.
Yeah, that's a really good summary. There aren't that many choices for this particular.
No, there's not many. Some of the new Chinese ones are interesting though. I haven't gotten into that much, but I've seen some interesting products appearing with some of the GoWin ones and things like that.
Yeah, it's those are definitely well worth watching. But yeah, I think the choice is really pretty solid, and this particular design is I think it meets all of the sort of requirements that you've been talking about. I know it's always very stressful to go ahead and kind of make a decision and to go turn it into hardware. But I just like to encourage you and to sort of speak up in defense of this choice. Just the choice of the processor with the ICE40 is great. And the care that you've taken to make sure that it is configurable and useful for experimenting and for development. You've delivered. So go ahead and make some boards. Whatever form factor needs to happen for FunCube at this point. If you do it, it's going to be super useful for all the rest of us. You know, Oscar agrees. So please proceed. And you've got. We'll help however we can. We'll move forward with the with HDL. We'll keep working on the simulation of the channelizer and the receiver for the successive interference cancellation sort of approach. If anybody else wants to pick up a little bit more on the communications, some traditional communications modes to see how it would work for that, which it will. then that's totally open for anybody to kind of pick up and move forward on. But I think that we'll have some actual simulation, some HDL simulation pretty soon. I don't want to promise the next week exactly because there's a lot of things going on in the next couple of days. So it may be a week or two that we have any sort of.
I've taken great care throughout this project not to promise anything to anybody.
That's a very
because
thing to do. Yes, I have. Yeah. But we're really pretty close. The work that you have, that Python notebook, pretty much that was a lot of like, neural activity there and some review. 4 or 5 different folks looked at it and helped me out. And we flogged it as hard as we could. And then I think moving to actually getting some traction with
I
HDL
think it's going to be really interesting to see what that ends up translating to as sort of LUT count on the
Yes.
ICE-40. That I think will tell us a lot.
Yes,
Give us an idea where we're sitting.
Yeah, that's the number I want to get back to you as quickly as possible, because when we look at Opulent Voice and see the sort of the history of how many loots it consumed, in some cases we were grossly overestimating how much space it would take, and in other parts of the design, grossly underestimating how much space it would take. And then the loot count is one thing, but there's other parts of an FPGA that matter. The type of design that you have, if it is sort of heterogeneous and does a bunch of different types of digital design, it can consume the sort of the management and the routing, that the place and route part. So instead of the synthesizing into actual digital assignments, that might be pretty efficient, but the shipping around of the data within the place and route turns out to be the problem. And people with a lot of experience here can sort of kind of predict what they're going to get. I'm pretty sure Matthew would agree to this. So over time you get kind of an instinct on, oh, this design is not going to be very efficiently routed in this class of FPGA or this brand. So we'll find out pretty soon, because that's the number I'd like to get back to you quickly. Based on our estimates, it looks like it's going to fit. The good news is that I know for a fact it doesn't really even matter what kind of FPGA you have, but a polyphase or multi-rate sort of processing type of design is a really good fit for FPGAs, both for utilization of the loots and also for like slicing and placing and routing and the interface. So I'm confident, but you like you said about the schedule, you never really want to make a promise that you can't completely deliver. So I want to get that number to you as quickly as possible, meaning that means that we need to move from the Python notebook phase to, it might be a messy draft. It might not completely work. It won't be the final design, but you start to get a real good gut sort of, you get real good results of like exactly how much is consumed in the chip. And we can do that with the tools that we have. We don't need hardware to target. We just tell Vivado we want to target this, the ICE-40, and tell us how much it would consume on the ICE-40, and then deliver to you like, here's the utilization report. Here's how it's consuming things. The big problem will be shipping data off and on of the FPGA. We've gotten kind of accustomed to the Zinc, which has a hard processor actually in the fabric of the FPGA.
This is my big concern, because that's great when the two actually sort of link together like that, but here, I've actually got to put in buses between the things, and
right.
That's going to consume some amount of resource. Hopefully not too much, because we're talking pretty simple serial buses and so on.
Yeah, I think so far, just a back of envelope, it's a fact, but we're good by a factor of like 32, what we got so far, but who knows? That's a very high priority to get that number to you to actually ring it out and to deliver it so that we can start making some decisions about, because the interfaces are, door edges and doorways, that's where they get you. So that's what we'll prioritize.
Yeah.
And all of this applies to our receiver for Hyperaia. This is exactly sort of, we don't do successive interference cancellation. We just do channelization. So this challenge for FunCube Plus is actually more work and more difficult than a multi-rate channelizer receiver, which is what we're wanting to do for Hyperaia, so that we can take all of that Opulent Voice, channelization, channeled signals, and then deliver them to the work that Aaron's most familiar with, the downlink, DVB-S2 downlink. So, our job is just, we have a communications channel. Your job is you're asking us to be more like a spectrum analyzer. You don't know where the signals are, and you have to go find them. Versus,
but that also is not a functionality we have to launch with. It's a functionality it'd be nice to know that the hardware is capable of with some more development. But at launch, we want two things: some sort of simple transponder and the ability to update it on orbit. That's the key thing, right?
Okay.
Because if we've got that, then we can spend years playing with, okay, what other cool stuff can we write for it and send up there? To let people play with maximizing what you can get out of this hardware. At this stage, it's a question of, first of all, what hardware to fit the power budget. It sounds like we've converged on, the idea there. Okay, how can we use that hardware to achieve what we need to at launch, right? Everything else, like what more can we do with that hardware, could be much later.
I don't know a whole lot about on orbit updates. My knowledge here is limited to terrestrial updates of equipment, and that's pretty dated, 15 or 20 years ago. But I get the basics of it. It's challenging, and go ahead, Oscar.
I need to go. I'm sorry.
Oh, sure.
Just a few minutes.
Okay. Anything that you have to ask or to tell us about?
No,
Okay,
thank you.
Hey, thank you so much for coming. I'm really looking forward to the next year. All right. Anybody else with anything that they want to talk about, or any questions they have, or any reports that they have?
Hi, Nkosi here. So this,
Yeah, go ahead.
well, in particular for the Hyperaia system, what's the timeline in terms of that? Like, do you guys have any, projected timeline before launch, or what's that about?
Oh, that's a really good question. So our goal for Hyperaia for the open source GeoHeo, the what we call the full satellite thing, is to prototype it over the next year for 2026. And this is oriented to provide designs, open source designs and prototypes and demonstrations, live demos to the European Space Agency through their Future Geo program. So that's kind of the motivating goal, because it's always been as soon as possible is how we've approached it. But this for 2026, we're looking towards the ESA for kind of the framework of a schedule for delivering demonstrations and prototypes. Now, is there a launch associated with Future Geo? This is a funded ESA sort of endeavor to directly benefit the amateur radio satellite service. They looked at the QO100 satellite and they said, wow, that's awesome. What can we do to make this happen again? And to also broaden it, if at all possible, to outside the EU and the Middle East, which is the SHALESAT 2 satellite is where the QO100 transponder is hosted. This is a really neat project. So if those listening are not familiar with it, then look up the QO100 satellite. It's has a predicted 15-year lifespan, but it'll probably go past that. So it's a very active first GEO amateur payload that we've ever had. So very exciting. So ESA looked at that and they went, hey, how do we get more of that? That's pretty awesome. And this is one of those programs. So there's some funding. The workshop that happened in this past October at AMSAT DL symposium was one of the events that the ESA has kind of come in and helped support. What they're doing is collecting as many different designs as possible to try to organize as many different organizations in the amateur and open source community as possible. So we're active participant there and have committed to be part of the process, along with a lot of other AMSATs and individuals and open source amateur folks. Okay, so that's kind of the context. We decided that going with that and kind of saying, okay, we're going to now deliver prototype demonstration in the context of the Future Geo program. And this just works to our benefit. It gives us a goal and an audience and some organization and some feedback, which is really kind of important. So the goal, that's the sort of the prototyping and the demonstration goal. That helps us out a lot, continues the work that we've been doing for the past, it's now 5 years of work that's built to this level.
Mhm.
Now, in terms of a launch, the ESA wants to facilitate a launch. There is not a launch scheduled. So I just want to be super clear that there is no planned launch today. That this is something that they want to help organize. And ESA, of course, has lots of contacts with lots of different, suppliers and, companies. And, this will undoubtedly be, it will involve commercial companies to make a geo satellite for amateur radio. And that the odds of like us having to build it or homebrew it on a bench are a little lower. So by sort of interfacing with and delivering designs to Future Geo, this will result in a commercial transponder, either being custom designed for amateur radio like QO100, or something being modified, an existing sort of commercial transponder. And for our point of view, for Future Geo, what we've been telling the Future Geo kind of consortium of amateur organizations and interested individuals is that there's 2 ways to do this. Linear transponder, just a bent pipe on the amateur bands, very similar to what you can get with QO100. But also there is this other way of looking at it, which is the way that we have designed it. It's as a multiplexing digital based system where you receive a bunch of channels and you do lots of digital manipulation and improvement. You have forward error correction, you have coding gain, you have quality of service, you have prioritization, and then you package all of that up and you retransmit it from the satellite. So not just a bent pipe, but you actually put more of the processing and the receiving and the transmitting on the spacecraft. So those are the 2 big approaches. You have to choose pretty early on which one are you going to have. And you can have both, sure. But we've seen in the past that once it works from a more conservative linear transponder sort of approach, that no one ever really kind of pushes forward, and they don't really take the perceived risk of putting a fully capable digital package into space. So we're coming down on the side of go ahead and have a more complicated system in space, and let's go ahead and design something like High-Firia and offer that. So we will be demonstrating and prototyping that to the ESA for 2026. The next meeting or workshop may be in March, but I don't have a date or a time for that. There's some other big events later in 2026 where all of the principals usually kind of already going to be at. And I've spoken up and said maybe we should just plan on meeting at events like symposiums, AMSAT DL, or wherever, Friedrichshafen. If there's any sort of place where people are already coming, that we shouldn't have to then also attend a whole separate other big event for Future Geo. So as soon as I know anything, I'll come back. I put out the call and kind of asked if anybody was going to be at FOSDEM, which is coming up on the 31st of January, 1st of February. And I've told them that that Everett's just going to be there. Look for him, reach out in any way, try to get in touch with us, and we'll just move things forward. If we have to prototype and just record it and put it out on YouTube and say, here you go, here's our working design so far, pointing at the stuff that Aaron has done, all the stuff that we're doing in remote labs, that's what we'll do. And we'll speak up for the sort of the digital side of the ledger, so to speak. I think it's pretty clear that a bent pipe will probably work just fine. But it's 2026 and we should stick up for digital techniques and for the tremendous amount of like coding gain that you get from a more capable and modern payload. So I hope that answers the question. There isn't really a launch that we know about. On our own, we cannot afford a launch to schedule one just on our own. As soon as we have a fully functional end-to-end system, I promise you I will start nagging people to start like, hey, here we've got this. You could use it. It's open source and you can adopt it. And I think that we'll see we've already seen a lot of interest here. Parts of our designs have already been used, and I think we'll get some traction there. So no specific particular launch on our schedule that we can pull off, and the future GEO folks in the ESA do not have a launch scheduled, but it is absolutely a priority for them, and the work that we're doing is directly feeding into the future GEO sort of process. Is that
okay? Oh yeah, it does. Because I was curious. I know for certain launches, you can't just do it like 1 or 2 months out. You have to actually schedule half a year to a year in advance. But I was just curious.
Yeah. Some of these schedules are many years. Somebody, Mike Parker, that drops in and to this meeting pretty frequently. Most recently involved with the CatSat satellite up and running, and it has a 5 and dime sort of microwave amateur payload. This took years to get going and had some pretty significant delays. And I'm sure that Rick and Paul, Matthew, and me at Qualcomm with Globalstar, Tim, we all have seen that it takes a long time. It can take a long time to get your payload put together. Looking back a little further in our history, we had what looked like a really good opportunity to get a hosted payload on the wide field of view satellite for phase 4. And it did not work out because the Air Force, the main payload, was delayed and delayed and delayed. And then eventually they were like, oh, we can make money if we kind of sell this space rather than donate it to amateurs. But that design lives on. The things that we learned from the design and the very, very positive feedback we got from presenting the design to the Air Force for them to kind of approve it and say, yay or nay, are we going to let it on our satellite? All of that was very, very positive. So you just have to keep coming back and trying. And yeah, it can be multi-year delays. I think Martin can probably speak to how long it's been between different FunCube launches. Just from AMSAT UK's very amazing history as one of the most successful AMSAT organizations out there. It can take a long time to get something in orbit and to get it through like all the different regulatory processes and all the different technical hurdles. So yeah, you're exactly right. It can take a while. And just got to keep showing up and kind of keep hitting the dumpster fire with a tire iron until it goes out.
I hear you.
Any other concerns, comments, questions, anything, any stories or reports? Floor is open. Rick, anything from DSES science meeting yesterday?
We are concerned about things we don't know. So tomorrow morning, there'll be an international meeting, worldwide meeting of the 35 participants with NASA and NASA promises to answer all of our questions. Our questions right now have to do primarily with steering data and scheduling. How much information at what points, how do we bundle the information when we send in our results, because they're packaged in these files with headers and a bunch of data. Is that an hour's data, a day's data, 10 days data? You know, how quickly do they want it? Is it near real time, or you know, there's so much we don't know. And yeah, the mission could go up in a week and a half.
Yeah, and for those that aren't familiar with this is the Artemis II tracking challenge, and it was a competition that was open to anybody with a capable enough station to kind of apply to be a first line reporter for tracking the launch and everything. Does that capture the big picture, Rick?
Yeah, we're providing NASA with data that will help them track the man's capsule on its way to and from the moon. So it's an interesting project. I was very pleased now that the public announcement has been made. There is a web page on NASA's site that lists the 35 participants that have been chosen to work directly with NASA. And one of those participants is the University of Zurich. And the point of contact for the university sent me an email, said, Rick, we haven't talked in years. I've been busy. I've got a new baby, this and that and the other things. And it was like old home week. I said, oh my God, Akeem, I haven't talked to you in like forever. We're AMSAT pals, or astronomy friends, you know, and he was fully aware of Deep Space Exploration Society and all that we've been doing. He's been keeping an eye on us. And so I was very pleased that at least I have a good friend from the good old days at one of the 35 sites. So I sent him my list of questions, and he said, we don't know the answers to those questions either. Let's hope NASA can provide some answers.
Yeah, I know that there's a lot of questions. It sounds like it's
Well, I boiled it down to like 6 questions,
okay.
you know, trying to get down to the essence.
Very good. No, I'm really looking forward to all of this. And I know it's a big endeavor, and you have to cover many days. So
The biggest thing is, you may have noticed that I appeared not to be paying attention. I was listening. But the donated master clock for this project, the HP 5065A that was donated, is broken. And just now we have repaired like 5 things in it, but the final thing is something that cannot be repaired in time for the mission.
oh wow.
And I'm really disappointed in that. But that means that I'm going to have to take my commercial unit out of service, shut my company's main productivity item down, and just donate that to the cause. Unless I can convince this gentleman about an hour's drive from here to donate or to loan us a cesium oscillator, HP cesium oscillator, which appears to be in working order. I'm hoping he will.
Wow. Never a
But
dull
otherwise,
moment,
I've got to donate mine, and that's going to be painful, but it is what it is.
Wow. Okay. Well, it's going to be not just good science, but some good stories, that sounds like.
Yeah, our RF package is coming along beautifully. We will be at Haswell. I'll be there Saturday. and other people will be there Friday, Saturday, and early Sunday. We'll be testing the final RF package. We have a main package that Alex is providing, and I'm providing a backup RF package. So we'll be able to make measurements from independent hardware simultaneously. That'll be interesting.
Yeah, good.
And so there's basically the antenna steering team called System One. There's 3 people in that team who are working out the details because the steering has to be more precise because the frequency is twice what we normally use. So our beam width is a little less than half a degree. So we can't just point at the moon and hope to capture everything. We have to actually track very carefully throughout the mission. So the steering team, the RF team, the time and frequency standard team, that's Ray and me. And finally, and most importantly, there's the group of people who we need to man the site for 10 days. We've never done that before, and we need at least 2 people on site at all times. That's our minimum for steering the antenna. We won't steer it remotely. Everything else can be done remotely. But that we don't allow because
Yeah.
if anything goes wrong, we want someone on site, and we want 2 people on site in case something goes wrong with the first person, that there's a safety valve because we're probably 45 minutes from the nearest emergency room.
Yeah. No, it's pretty similar to like Palomar Mountain. That's all.
So we're trying to get volunteers. Not every volunteer has to be an expert at steering the antenna. They can be the backup person and learn and be the safety person, but that we need 2 people at all times for 10 days. And we don't know what 10 days. So don't ask me, ask NASA. 10 days starting when the launch occurs.
Right.
We all know how that goes.
Yeah. No, very good. So we oh, go ahead, Adrian.
Yeah, I was going to say, one of the things that, excuse me, worries me, just looking at the very crude trajectory figure that NASA has provided, it really looks like what I think is probably one of the most important points, data points that NASA might be interested in, is actually the at TLI, and it looks like that might be occurring sort of towards the southern Pacific part of their orbit. And so I'm not sure if DSES will be able to acquire that. It might be below the horizon at that point. It'll be interesting to see exactly when the translunar injection burn occurs. And it seems to me that that's one of the most important points, is that's going to be the primary determination of their trajectory. I know they probably have some other mid-course corrections out on their way, but those are relatively minor. So it'd be kind of curious to see exactly what those coordinates are going to be for perhaps DSES being able to acquire that signal at the time.
Well,
so anyway,
as you say, if it's not in view, it's not in view.
Yeah, right.
And if it's over the South Pacific, there's none of the 35 stations will be in view.
Yeah.
And
it would have to be.
We're not the primary trackers anyway.
Yeah, it would be like Australia or something. It would have to be Canberra or something like that would be tracking at the time. So,
yeah,
but none of
they have the Deep Space Network or some network working on actually capturing the telemetry. We're not allowed to do that. The telemetry is encrypted. And so, if they have their primary sites, this is something else. This is an all volunteer group of
Right.
universities, private individuals, commercial groups that are going to provide data that will help them track the mission. It won't provide telemetry data, so we can only assume that they have, their own assets for that. So it's not
Sure, yeah.
just us doing it, but for us, it's a very interesting science experiment.
There's a related science experiment coming up in October, Earth, Venus, Earth, but in the past, the Earth, Venus, Earth return has been, just radar return from, and we're transitioning from, or attempting to transition from that to actual recovery of communications from bouncing off of Venus. So I'm hoping to see some Eve work with DSES kind of move.
Well,
Hopefully, the work here that you're doing will be leveraged for that as well.
There have been some very eye-opening experiments done in the last few weeks. First of all, the dish was designed for tropospheric studies back in the 50s. So it was designed to operate below 2 gigahertz. And so for the decades we've owned it, people have debated, well, what is its upper frequency limit of effective utilization? And last weekend, we have another project to try to obtain signals from the Mars or from the from the deep space satellites at 8.5 gigahertz. And so the 8.5 gigahertz system was put up, a beacon was assembled and deployed 10 miles away, and it worked. And it worked as well as the predictions of if the dish will work properly at that high frequency, then what would it do? And it performed almost flawlessly to the predictions. So that was one thing. So we now are pretty convinced our highest frequencies had been pulsar work at 1.6 gigahertz. And now with the 8 gigahertz beacon tests and calibration tests, we now have a pretty good idea that the dish, when we steer it, can be steered to 1/10 of a degree or less, and that it works at 8 gigahertz, which means that for EVE, that's 2.4 gigahertz this time instead of 1296.
Yeah.
And so we have great confidence it'll work.
Yeah, that's really not surprising. And I'm very, very glad that there's some good proof there. But yeah, the 2304 or 2400 or 2410 or
and of course, this project is 2200.
Yep.
And it will further validate our ability to steer as the frequency goes up, that beam width goes down.
Yeah.
And can we steer better? The answer is yes. We've learned that. Can the dish work at the EVE frequencies? We've absolutely confirmed that in the last week. So
yeah, I think that matches the prediction. So
yes, everything we've done so far will have gives us positive feelings about EVE.
Good.
Because 2.4 is nearly the ideal frequency for bouncing signals off of Venus. 1296 was not the ideal frequency for its reflectivity.
It's true. It's not bad. 1296 isn't terrible, but the right frequency is a little closer, a little above 2 big.
With that particular project, every dB is a big deal.
It is. This is a daunting channel, and it will take a lengthy integration, and that's really kind of the limiting factor is, because you're talking about, well, if the moon ain't up, then you're not going to be able to track Doppler for something around the moon.
Right.
Same thing for Venus. It is only up a certain fraction of the day. And if your integration time is days and days, then that's not, that doesn't immediately look like it's going to work. It will.
Well, even then, when Venus is up, a lot of the times it's just right off the sun.
Yeah.
And if we point our antenna at the sun, things burn up.
Yeah. We don't want to do
It's we don't want to point at the sun. So that was a limiting factor during the 1296 test too, because Venus was up during the day, but so was the sun, and
right.
they were nearby.
Yeah.
I haven't looked to see what October looks like, but I think we'll still have that problem.
Yeah, I think we're going to go ahead and start publishing some plans. Some, we're talking about geometry now. So
Well, the
go ahead and
the
start publishing, like, this is what it's going to look like from these particular sites in the notebook, in the Eve notebook.
Yeah.
And here's basically the windows of time. So do you have 2 hours, 6 hours? How many hours do you have? And we already know that is going to be pushing it real hard. So I think we'll get some answers, and how close can we get to being able to integrate, because it is an integration challenge. That's very, very clear. To be able to recover information, so not just a carrier tone, but to actually get a transmitted signal, and we're talking about maybe bits. So not kilobytes or megabytes or anything like that, but we're talking about a relatively modest amount of information to get through the channel.
Yes, I think we want to see that simulation window. Just came up on the chat there.
Yes, that's what we're going to add to the existing notebook. Oh, proof of. Awesome. Okay. Yeah, that's in the near future for Eve, is to get that done. And we do have some really nice work from a couple of different volunteers and from SBMS on kind of nailing down exactly what the correlation windows are, and what the limit is. And we did see that reflected, pun intended, from the EME work that Thomas Telkamp was able to carry out. So those sorts of experiments to kind of, okay, turn the power way down, bounce it off the moon, see what happens. Are you seeing the same sort of things? That's going to be helpful. So yeah, that sort of stuff is proceeding, and I think the big risk here is transmitter power. To not overheat our transmitters next time around, to be able to actually have a few more tests of the transmitter, to have backup transmitters, because it we're talking about a significant amount of power and
Yeah, I think
equipment, and if you
I
only
think
have
we're
one copy of
talking
it,
our design right now, I think is five. I think it's 250-watt transmitters to be combined into one output of 1.5 kilowatts. So they'll be, they won't be pushed to their limits.
right? No, that's good.
it'll be it'll be interesting to have all the results from not only Artemis but also Eve for several years from now for Apophis.
Yeah.
Because the tracking and then the Eve work with the signal will be interesting to see if how that works out for that attempt.
Yeah, didn't we run the numbers? That actually looks very doable. I remember, because when you raised this in a couple of meetings ago, that we looked at the numbers, and the link actually is, assuming you can track it and design a signal, that it actually will work. The link budget works out. That's going to be a really exciting thing. I know that Rick has looked at this too.
Yeah, one parameter I don't know, we need to measure it, is what is our tracking speed
Right. Yeah.
And
It's
tracking
a little
speed
faster
is,
than Venus, I think, is
well, I think we can track Venus.
I know,
We
but
cannot,
the apotheosis or what is like it's faster, right? That's
yeah,
a
we cannot do
Well,
Leos.
right. Yeah. No, that's pretty
well,
quick.
that's why I was mentioning Artemis, because that's going to be moving pretty quickly. Also, especially close in. So that
Well,
might
the
be
chart I
a
saw
challenge.
last night suggests that very shortly after injection burn, it will not be moving quickly
Right.
relative to us.
Right. Yeah. It should be
It will
actually pretty
start
close.
moving away from us, and therefore we won't have much trouble tracking it. I do not expect us to be tracking it before lunar injection.
Yeah.
Yeah.
That makes sense. I have a question.
There are, of the 35 stations, some of them have much smaller and more agile antennas. The NASA RFI specified antennas 9 meters and up.
Yeah.
Well, ours is a lot bigger than that. I expect smaller tracking antennas to be more effective when it's close to the Earth, and we're not gonna beat ourselves up about it.
One of the things that you're going to learn for this through the Artemis sort of mission is staffing and support of people actually coming out to your site because this is going to come up with Eve. What we really want to do is start, you know, trying to bounce signals off of Venus well before the inferior conjunction to kind of like just start doing it.
Yeah,
Like budget may say it's out of range, but uh, to not just limit it to a couple of hours, to try well before and actually well after the actual inferior conjunction. So, sort of learning how to get people out there, how to keep them out there for longer than a weekend, I think is going to pay off. And there are other sites out there that'll be involved in the effort where it is pretty much remote too. Sites that do not have facilities at the site, and then there's sites that do have facilities that have people there all the time. So there's a whole variety out there in terms of staffing and support. But the things that you're learning for having to do a 10-day event or have a 10-day window of operations, I think are going to help us out a lot with the eventual success for Eve because it's going to take over time multiple lengthy sort of like runs, transmitting and receiving, listening for other people's transmissions.
and a lot of this happens at night,
Yes.
and that's going to be true here also. And so right now, the last few sessions out there, people have brought air mattresses and things so that they can sleep reasonably comfortably on the floor in our sort of auditorium room. And we have hookups for RVs. Well, we have power hookup. We don't have sewer hookup, but we have hookups so people with RVs can plug them in and be comfortable. And then one or two guys sleep in a motel that is giving us favorable rates, discounted rates for any time we show up. And the downside of that is it's 30 miles away to the nearest motel. There's nothing really close, but still. So our guys have
That's
figured
actually
it out.
that's comparable to Allen Telescope Array.
Yeah.
It's a half hour, 20-30 minute drive to your if you don't get one of the dorm rooms
Yeah.
at the ATA, which are very rustic, I have to say. If you don't get one of those and you want a
We're
hotel,
not that bad. We have a real bathroom. We have a shower. We have a kitchen, a microwave, we have a small refrigerator. We're not that rustic. We're okay.
Yeah, it sounds like a pretty similar to ATA. It's a dorm style thing. You can stay. It's not just the control room and then no
Yeah.
facilities, which
No.
does kind of limit it to, you're going to visit for a day. It's a day trip, So, I mean, having a place with it, having the hookups for RV is a real big deal. So it's essentially dry camping, but that's very doable. So I'm looking forward to the experiences that you all get with this. It sounds like in many ways, not just the technical side, but also operations and support. Human resources side will also help with a solid effort in October. So
And
we're
every
very
now
much
and
looking
then
forward to that.
I find hams who are also private pilots. I used to have a private pilot's license, but it's not current. We do have airports in the neighborhood out there. Why? Because if you're a rancher, how the
Yeah,
heck do you get downtown?
yeah.
You fly. So there are anywhere from moderate to substantial private plane airports that are close enough that you can be picked up.
Cool. Well, I'm looking forward to this. I think it'll feed directly into the Eve effort, and we'll just keep publishing and reaching out, working with a number of other.
I think you and Paul should drive out here. It's only about a 4-day drive.
No, it's not that far, really. It's
Now,
not 4 days.
if you were sharing the driving, you could get here in 2 days.
Yeah, it's not that far. Yeah, we'll see.
You could do it in 2 days, even with one driver. So
Yeah,
it's about 12 here to where we're at, and then another, I think it would be 8 to Haswell from where we're at.
yeah, easy.
See, no problem.
Right on. Okay, well, thank.
Well, the closest members of VSCS to Haswell are me and Ray, and we're 2.5 hours one way.
Yeah,
So yesterday I said to Ray, I have to go down there Saturday. Will you please ride with me? I just don't want to do a 5-hour drive in one day without somebody to talk to. So he
right.
said, yeah, well, I'll go.
Yeah, for those of you not familiar with Haswell, it is way out there. It's a remote site for sure. You know,
We
a lot of
don't have
us are
a
used to
whole
like,
lot of RFI.
right. Yeah, it's a quiet, radio
You
quiet,
know,
sure.
we do have RFI when we point the antenna straight up, because I think the military has figured out that that's a good place to have exercises,
Yeah.
and they do a lot of 200 megahertz stuff.
Yeah, a lot of us that are very active on microwave are used to the links being somewhat shorter. The terrestrial links for microwave and for like the microwave contests. You can go out and you can either be on a mountaintop or you can be a rover and you have schedules and everything. And but so we're talking about Haswell. It's like it's way out there and on purpose, not by accident. And it's a really neat resource for amateur radio and for amateur astronomy,
We'll
especially.
talk about RFI. We're not doing all that well here in San Diego, Michelle. The Miramar people kind of. I've sort of done some just a little bit because I'm trying to see if I can do some hydrogen line work since I'm also a SARA person, and just doing a little bit of survey work with just a loggy on the SDR, just kind of panning around. See, besides the local sort of cell phone towers, boy, anything I point, I'm kind of a bit north of Miramar. So pointing out to Miramar, the noise level just goes up exponentially, around 21 centimeters anyway. So yeah, RFI here is not great either. So
It can be
that's
pretty
a
challenging.
challenge.
That's true. Yeah, the difference between having because Paul has a HF station here, in essentially suburban San Diego. And then I am able to I have access to roughly equivalent station on Palomar Mountain, and it's a huge difference in the noise floor. And that's on HF and not at the hydrogen line frequencies that you're talking about, but just across the board. Anytime that you're near an urban setting, the RFI can be very challenging, can give you a run for your money.
Speaking of microwaves, I'm sure you've heard of the loss of our beacons up in
Yeah,
Mount Miguel. That really hurts
it does.
because they were really useful for just uh, getting stuff lined up on some of the handbands up there, even up at the 10 gigs. But anyway,
Yeah, it was a good run while it lasted. I think Paul had some information that there might have been worked out, that those beacons might actually go back on the air, but I have not seen that shared publicly.
I hope so.
Yeah,
I
it'd be
hope
nice
so.
to see. This is great, and just really appreciate all of you doing all of the things that you do, and we'll keep it up. So I'll open the floor for any last comments or questions before we close for the week, and then we'll do this again as soon as we can. I do have some updates there's an IEEE standards group for drones that we're involved in, and it's been a interesting experience. The meetings are now going to go to much more often, and we will be contributing there for physical layer and for command and control layer for advocating open source solutions and some, actual implementation and network and ambient access sort of things. There's a lot of other R&D stuff going on and some regulatory work. So we'll meet again in a week, but I'm going to open the floor up for anybody that has any things to share before we close.
Tim Cash. I really appreciate listening to what you all are about, and I thought people like me were pretty much gone and forgotten, and this makes me. I recall the good old days. I mean, I attended two of the launches of the Apollo Saturn V and the last one of the Skylab workshop, and I've been involved in space since 1960. As a devotee and since 1980 as an aerospace professional, and to see it still happening with the passion that it takes is very heartening, extremely so to somebody like me. And I also know a lot about RFI, electromagnetics, EMI expert for my job at Northrop Grumman. And so I know what you're talking about. Making those measurements are difficult at best on a good day. And it's hard when when the environment doesn't work your way, and which it often does not. So I would like to just thank all of you for your passion. And I hope to be part of this through Samudra and Tech Terrain LLC. Thank you for the opportunity to attend.
Oh, of course. You're very welcome. And thank you for the kind words. It makes all the difference in the world. Thank you, Tim. See you again soon. And we'll
Sure.
be. All right. Anyone else?
Do you want to see some simulation waveforms just for
Yes,
fun?
yes.
Yeah, that'd be great.
All right.
Please.
All righty. So this is a simulation I have. I just finished this a little bit ago. And just to give some context here, this first analog waveform at the top is the PI controller loop filter. So this is where there's a frequency offset in this particular simulation. So the loop filter, you could see it's moving down, 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 and about here it flattens out, and that's basically really our lock point, I would say, because from here on out, the loop filter you can see is very stable for the remainder of the simulation. And then what we do is to detect the lock, we take so this is a Costas loop that we're looking at, a single one for the F1 frequency. And we take the I arm, which is the data arm, and we take that value after we've accumulated, so each symbol we accumulate on the I arm and the Q arm. And so here we're taking that I arm and Q arm accumulation and we're squaring them. And so you can see the I arm here kind of pops up and down and then kind of flattens out at the top, again, for the duration of the simulation. And then we have, and then we accumulate that value. So you can see that we get this kind of sawtooth wave, but it's muted a little bit at the beginning of the simulation. And then it gets to a similar value for the remainder. And then the Q arm is really the error arm. So the I arm is the data and the Costas loop. The Q arm is the error signal that we're developing. And so again, we square the Q signal and we could see it pop up and bounce around a little bit, and it finally flattens out. And again, if we take so here's the Q accumulation, right? It initially shows that sawtooth wave, but then it flattens out and goes flat. And so this is really kind of our lock point exactly, because the error signal should be near zero. And so we can see here, it's not zero, but it's relatively small compared to the I arm. And so what we're doing then is we're going to take this at the end of each accumulation. So the sawtooth is the accumulation period. We're going to take a delta from the I and the Q, and then so that's this plot here. So it's kind of small at the beginning, and then it pops up and it stays high for the remainder, which you kind of would expect. And so what we do is we're setting a threshold that once this delta exceeds a certain value, we declare lock. And so the value's here, and we can see a lock being asserted right there. Then the accumulation period for this particular simulation is 128 symbols. We can make it longer or shorter, so it's something that we can tune. It'll be a configurable parameter as well as the threshold. But we can see if we go back and look at the loop filter accumulation, we've really kind of flattened out right here, and we've declared the lock. But we've really accumulated starting from this point, right? So we're accumulating the I and Q from here, but so we can see the loop filter. It's getting pretty close. It's not quite down there yet, but it's close enough that we can end up declaring lock over this particular accumulation period, because we get down during this accumulation period pretty flat. So anyways, that's kind of what we're doing, what this initial design is doing. And so it was a proof of concept. I'm pretty happy with it. Probably needs some fine tuning, but it's even something we could take in the lab pretty soon and see how well it's working. So
wow,
was just something I wanted to share.
No, thank you. This is a great tour. I think it's like popping the hood and looking at all the different engine parts. This is really neat. And it looks like it's well within a frame, even without like digging in and optimizing all of the things. There's lots of levers here.
Yeah.
But that's
about 12 milliseconds, or maybe 13, right?
awesome. Okay. That's really good. Wow.
This is noiseless, right? So I mean, it's kind of ideal stimulation, but we do have a frequency offset. If there was no frequency offset, it would have happened much sooner. But so I mean, there's a little not impairment, but real world effect here with the frequency offset. But yeah, it does lock pretty quickly relative.
So are you saying that the error was 12 to 13 microseconds, or the signal?
Well, what I'm saying is, so it's 0 is when we're starting the simulation, right? And during that 12 milliseconds or 13 milliseconds, we can see the loop filter coming down and getting to its kind of quiescent value. And then, and so we're effectively with this particular lock circuit, we're declaring lock at about the right time, right? Given the accumulation duration. So if this was, say, 256 symbols instead of 128, we wouldn't declare lock until the second peak, because that would be one longer accumulation, right? And then it would be closer to 18 or 19. So the lock point, right, is a bit dependent on how many symbols we want to look over to see the to accumulate across and doing the calculation.
I see. Yeah, that's a pretty decent thing. I have to assume you're using Linux for this product.
Well, this is a VHDL implementation, and so this is a VHDL simulation of the actual RTL that would go onto the FPGA.
Okay, thank you.
But it is using an open source simulator, which is NVC. There's a GHDL simulator that's available too, but NVC is a little bit faster. And then a GTK Wave is the waveform viewer. So these are all open source tools, which is nice.
This is exciting, Matthew, and it makes me think of new things that I want to ask for.
Sure, yeah. No, I mean that's the thing about this. We started out very rudimentary in the design, but there's lots of things that can be added and improved to make a robust design and more commercial like design, if you will, and that the features that are available. So, and this is a one aspect of the lock. I want to implement another mechanism. So again, we can see this loop filter accumulator trending down and flattening out. So another approach to this lock detector would be to take the mean of this signal and the variance, and then the variance, if it's within a certain threshold, if it's below a certain threshold, you can declare lock as well. So you can see if the mean here is going to be changing and the threshold or the variance is going to be relatively high, but then when we get down to the flat section, the variance is going to be very low relative to the mean. And so I think it'd be nice to have both implementations, and they could actually then you could AND them together so that you don't declare lock until both are there. So I mean, there's multiple ways we can do this. And again, like another thing I want to do as part of this, as I mentioned earlier, is adding a SNR detector, EVM detector, so we can actually get an SNR value that we can calculate and display.
Yeah, I would like to see that. I'm going to get spoiled by this kind of a diagram though, because I'm not going to be able to sample it that fast unless you provide me with a mechanism that logs all this stuff to a buffer, and then I can read it out.
Yeah, we could log it to a buffer. You can get the same diagram with an ILA as well. You just a little bit, a little bit limited necessarily in the how much you can store in the ILA, but it's kind of the same as the block grams. I mean, so you can allocate more block grams to get more buffer depth in the ILA. So yeah, but we could do both or one or the other. We could certainly collect statistics into a RAM and pull them out, or via an ILA would work as well.
Yeah, I would definitely want to see this without an ILA, I think, with as little overhead as possible, so that I can use it in a deployed radio and get some real measurements about how long acquisition takes in real world circumstances.
Yeah,
because
we could actually add like a lock count, right? Or so like when we assert, or from the time we think we should be acquiring, right? There's probably some mechanism we can use to the time we do acquire or detect lock. We can count the number of clocks, for instance, and determine that time that it takes to lock. And so if we have different impairments in the real world, we can see how that affects the lock time. And the other thing we can do is say we could capture some of this data, so we don't have to have so much. We could, at each interval, each accumulation interval, we could capture the values that were at the end of that accumulation interval. That would be a lot less data. You wouldn't see the sawtooth, but you would see where we were, and you could even compute the lock from that, right? Because you can it's just the I minus Q here effectively is as long as if that delta is above a threshold, then you have lock. But so I mean, certainly whatever you like that we can fit in, we can do that.
Outstanding. Is this in is this in a branch in the repo yet, or?
No, I just it's just in my local, but I can do a branch off main, and because I'm developing this off main right now, so I can branch it and push it to the repo, and we can start playing with it.
Awesome. Yeah, that would be great. Yeah, as soon as you're comfortable at all in going ahead and sharing it, then we can get that out there and start.
Yeah, I need to add the configuration registers. I'm just forcing the threshold and the count for the moment. So yeah, I need to add the CSR registers, and there probably needs to be some scaling, but it should work as it is. So I can even push it and then continue updating the bit widths and that sort of thing.
Awesome. Yeah, I cannot wait to try this. This is super exciting. Thank you. Thank you so much.
It sure be nice if we could get an interrupt when the lock indicator clicks in, but I don't
We could do that,
know.
sure.
Well, we can do it from our point of view, but can we do it without interfering with IIO? I don't want to have to read to change the kernel drivers that are taking the DMA interrupts, for instance. And if they're all multiplexed together, which I imagine they probably are, might be a problem.
Right.
We don't have any spare IO, as far as I know, on either of these platforms.
But I mean, presumably there's a interrupt status register that's read. But I guess is IIO reading that, or is something else reading it and calling back to IIO? So that would be my question.
We're not touching any of that stuff in our application code. So anything that's happening is happening in the IIO kernel driver.
Yeah, I don't think I'm using any of that either.
Can the IIO call another function? Is there some integration that it has that it could call out to some other process?
I don't know. I suspect that if that existed and was something that was safe to use, that it would be in the documentation. And I have spent a fair amount of time perusing the documentation, not looking for this particular thing. I think I would probably know if it existed, but a further search wouldn't hurt. If there's some way to get a general purpose interrupt or even just a general purpose status bit out, maybe you have to define it as a channel to get it out of IO. They have this general purpose mechanism for getting stuff out, but it assumes that that's going to be your main thing of interest, or one of several main things of interest.
Well, do we need anything at that level of performance, or can it be treated like the frame lock? Because it looks like it might be roughly same resolution.
Well, those are good questions. I think we might need a little more performance than a frame lock level, because at least we know how often the frame lock can change.
Well, I mean, we know how often it can change after we've established lock and we're just verifying sync, but we do a full-blown search from the get-go. So
yeah,
I think we might be able to handle it the same.
One thing about this, like if you have impairments, this was an early indication of a problem in the radio, right? So if the lock goes away, that's maybe much more interesting than the lock being asserted. In that, if you have a excessive Doppler, or if you have the SNR is very low, then the lock could be toggling or could go away, and that's the sooner you know that, maybe that's useful in the system level.
And I mean, for doing the optimization and doing the initial work of like proving out that we have all the gains set correctly, that we can understand the various channels that we're going to tackle terrestrial and space, that we'll need to know, we'll need to interrogate it more. I guess for like general, like when we deploy it, you're much more interested in, you're going to assume that it locks after we've done some work here, and we will need more visibility to get that to work correctly. But you're exactly right. The more interesting case is losing your symbol lock, And that is definitely something that we probably want to know about, um,
Yeah,
and plan
that's
for.
I agree. Another thing that's of particular interest is if you're almost in lock. Um, because if you're way out,
Right.
there's
Yeah.
no signal there at all,
Yeah.
then the software can actually do some good by intervening and resetting things to zero and trying to, it may know a little bit more about where the signal is likely to be than the modem knows until it finds it.
Yeah.
Yeah,
So
and you might need like, if the frequency offset's excessive outside the loop bandwidth of the PI controller, you could do a search, right? You could kind of step through some various frequency offsets and see if it locks at some point, something like that. And that would
yeah,
be
or even just
a good software assist.
Yeah.
yeah, if that might be necessary, or it might be enough just to slap it back to zero every time it goes too far astray.
Yeah, yeah.
In terms of ILA, I think we have, like right now, we can collect, gosh, I think it's depending on the clock, but this is all within the 61 megahertz clock and not the 245 megahertz clock. This is
Yeah.
all, so that
But
means
but
that we have like multiple bytes of collection power in the
yeah.
in the VRAM.
But we don't even have to go that fast or that fast, right? So if we look, we're only updating on the T clock, which is the symbol clock, right?
Ooh, okay.
So so
That's
if
really good then. So that's relatively very slow.
yeah, exactly.
Okay. Yeah, then we have lots of visibility.
Right. So
We can
so
get in
here's
there and
the symbol clock. So let me just zoom in. Um, right. So we're only updating it every 50, 54 kilohertz, that period.
awesome.
Um,
Okay. Yeah, I forgot about that clock. Then I think, yeah, Paul, we're in really good shape for collecting and being able to look at the operations like in hardware. I think this is going to be okay. I'm not worried.
Yeah. So I mean, you're right. It's a relatively small amount of data, relatively, because it's much slower than the system. Even the 66 megahertz clock, which I'm using here. Um, yeah. So you don't have to collect at that, and it doesn't even make sense to collect at the system clock rates,
Right.
because it's stable between the T clocks.
Right. Cool. This is great. All right.
Yeah, this is great.
Anything else? Any other questions from anybody about this really cool demonstration, or any follow-up or next steps from you, Matthew? What are you thinking about doing next?
Well, next steps will be adding the configuration status registers. And then I think the bit widths can be tuned. They're just really kind of um, brute forced at the moment. They're really wide. So like I'm taking a 16-bit from the I arm and Q arm, and then because I'm squaring them, they go to 32. But then I'm just staying at 32. Really, they can should be able to be resized down, and so it takes less logic. I'm not sure what the DSP slice is in the 7020, but in the FPGAs I generally work with, I think they're 24 or 28 bits. So if we want to put things into a DSP slice, it'd be much better, to get the bit widths down, especially so the square isn't 32, it should be more like 28 or 24, depending on the DSP slice. So it can be optimized with thoughts to the FPGA implementation in terms of bit widths, DSP slices. But so anyways, the bit widths I think can be tuned. And then, I just kind of empirically picked a lock threshold. Maybe that we need to do some more testing to really figure out what a good lock threshold is. Like I said, I kind of did it empirically, because if we look at the full thing here, I picked something that was more than these 2 points, but less than this point, right?
Yeah.
So just kind of eyeballing it. So we might, it's somehow, we probably should tune that threshold. Not sure it's something we really can do necessarily in simulation. Maybe That'd be something nice to do with real world scenarios. But we could, model this a little bit more. I think we could. I started this a little bit, but I think we could use a full Python model here because it would be useful for really testing more scenarios for longer durations than we can do in the RTL.
Yeah, no, that's a very wise approach. Well, this is super exciting. I'm looking forward to digging in and seeing how it works in hardware.
Yeah.
I've got a question that's related. Last time I looked at it, the power detector was not working in the hardware.
Yeah, right.
Do we need to look at that again, or do we know that there's a problem, or what's the status on that?
Well, we should look at it again, obviously, but I think should be here and should be working. There, okay. So like power squared. So this is the power detector, and we'll just get a decimal and yeah. So obviously very close to the beginning, the simulation. So we can see the power coming up and stabilizing at this 1755 value. I can't say what that is in terms of dBm at the moment, but or even dB. Well, it's really dBFS. So I think I put in somewhere the computation for dBFS based on this, but so it should be working. So yeah, I think when you read back this value, it's being read back as 0 all the time, right?
That was true last time I looked at it.
Yeah,
but we've changed a lot of things, including some things that made registers work better. So
yeah, I'll have to look. I'll look at the CSRs. I assume that there's just something maybe not connected or hooked up right, or some miswiring to the CSRs where we read this value.
Yeah, so we'll need this as part of the evaluation of the lock detector, right? We want to see how long from when the signal comes up to when the lock detector clicks in for various signal level.
Mm-hmm.
So, also needed.
Groovy.
Very much.
Yeah. Okay. Any last comments or questions before we close for the week? All right. Well, a very big thank you to Matthew for sharing this, and thanks for Rick for all of the updates, and everybody else that attended and made this a remarkably awesome meeting. Deeply appreciated. So yeah, we'll do this again. We anticipate meeting again next week, and there's plenty going on over the next week, as you can tell. So looking forward to sharing all of the feedback that we get from FOSDEM coming up. That'll be this coming weekend. So looking forward to that. All right, everybody. Thank you so much. See you on Slack. If you need anything, please reach out to me or any of your favorite board member at ORI. Any one of them will be very happy to help you get started or to get further along with your open source digital radio project. All right, so see you all soon.
Thank you.
You bet.